Hello, this is video 2 of section 2223. We're talking about derivatives, which are just instantaneous rates of change or slopes of the tangent line. And we're going to use tables to approximate these derivative values. So remember that this symbol is telling me to find the derivative of f at x equals 2. We're looking for the instantaneous rate of change of the f function at x equals 2. But the problem is I don't see an x equals 2. Well, that's okay. I'm going to choose 2 points that are close to 2. Now, I could choose 1 and 9, but that's not the closest that I can get to x equals 2. So instead, I'm going to pick this pair of points, this x and y, and I'm going to pick this pair of points, this x and y, because the x values are close to 2. So I can say that the derivative, the slope of the tangent line, is going to be approximated by the difference quotient. Remember, the difference quotient says subtract your output at 3 minus your output at negative 2 and divide everything by, I'm sorry, your output at 1, and then divide everything by 3 minus 1. So I'm using these 2 points close to x equals 2 to find the slope between them, and I'm going to say that's a pretty good approximation for the actual slope of the tangent line or the derivative value at 2. Okay, so that's going to give me 1 minus negative 2 divided by, well, 3 minus 1 is 2. And if I keep going, 1 minus a negative 2 is actually 3 divided by 2. And I just found my approximation. Now notice, my, my symbols here tell me that I'm approximating this work for this value. Or I'm approximating this value with this work. But this is the same as that, which is the same as that. So notice I'm using equal signs here because all the work on the right side of the approximation symbol is equivalent. It's just that the work and the answer that I get is not exactly the derivative, it's an approximation. Okay, well, let's try the next one. Can we estimate the derivative of f prime, at x equals 5? Once again, I don't see x equals 5. So I'm going to choose the two closest points to 5, which would be this one and this one. And I'm going to approximate this value with f of 7 minus f of 3 over 7 minus 3. Or the output or y value of 7 minus the output or y value at 3 divided by 4. And if you do this, you're going to get 1. And so we're able to take the derivative of, I'm sorry, we're able to take the derivative, approximate the derivative by using the difference quotient and getting some answers that are pretty good approximations based on the information we're given. As we're going to find out, in everyday life, whenever we collect data or whenever we're looking at a quantity, we're mostly collecting data, right? So they're separate points. So we're going to have to do what's best given the data that we're given. And so if we want to find the rate of change at a specific point, we're going to have to use the data points that are around that in order to figure that out. And that's how you take derivatives with tables. If I go to the back part, we're going to find the derivative use or approximate the derivative using graphs. Let's see. Using the graph of g of x, can you approximate the following values? Can you find the slope of the tangent line, the instantaneous rate of change, the derivative of g at negative 2? Well, I'm not a very good drawer, so I'm going to do this. And again, we want to approximate it by, I don't know where this, oh, this is getting worse. Would that line be a good approximation? Oh no, I dropped my mouse. Would that line be a good approximation? Maybe, right? And so what we're going to do is pick points on that purple line. So I definitely have one point that I know for sure. That's negative 2 comma 0. Can I pick another point? Well, maybe I can use 5, -1. No, that's too far off. Could I use 6? I'm sorry, -1, 6. Could I use that one up here? Maybe. Or maybe I could use -3, -4 down here, maybe. I could use one of those and we can figure that out. Or maybe we could use -1.5, 4. But do you see how I'm picking points that I think are on this line, right? What else could I do? Well, I could pick points that are on the curve and then use that. However, if I go too far, I'm not going to get a good approximation, right? If I go all the way to 0, the point on the curve at 0 is over here, and that's not going to be a good approximation. So I want to keep the points close, and so I think I'm going to just use the one at -1. This one up here, when x is -1, this line in purple is stretching. I'm going to say it's stretching all the way to 6. Is that exactly right? Maybe, maybe not, but I'm just going to use that as an approximation. So we're going to say this is about uh, g of -1 minus g of -2 over -1 minus -2, right? Well, g of -1, I said, was about 6, minus g of -2, we said, was 0, over -1 minus -2. Well, -1 minus -2 is really just 1, and so my answer is, or my approximation is, 6. So we're saying that the slope of this purple line is about 6. Is it? Well, we can argue whether that's close or not, but again, we're looking for an approximation, right? An estimate to see where it is. What about, let's do one more from this graph, and then we'll answer example 3. What about, let's do letter C. So for letter C, we're looking for the derivative. We're looking for the slope of the tangent line at x equals 1. Here's x equals 1. So if I draw that tangent line, it will look something like that. So I know this point for sure is at 1 comma 0, right? This point of tangency. Can I find another point? Well, I'm going to use this one maybe and say this is at 0, 3. And we're going to find the slope of those 2 points, because the slope of those 2 points would be the slope of this line, and this line is supposed to be the tangent line. So we're going to say this is approximately g of 1 minus g of 3 over 1 minus 3. Okay, g of 1 is 0 minus g of 3, I'm sorry, not g of 3, g of 0. Come on, Mr. Barrientos. G of 0. These are supposed to be x values, 1 minus 0. G of 0 is 3 divided by 1, and so I'm getting an answer, and my answer is -3. Well, this line does have a negative slope, so I'm confident there. And I guess it's about a slope of -3. I'm going to say that it is, and we'll go with that. So now that we found some examples like that, can you work backwards? What if I tell you that the derivative, or the slope of the tangent line, is equal to 0? The slope of the tangent line is equal to 0. Where is the slope equal to 0? Well, I'm looking at this purple line that has a positive slope. I'm looking at this orange line that has a negative slope. So where would it have a 0 slope? Well, wherever it changes from going up to going down, and that's going to occur right here. It has 0 slope. And right here, it has 0 slope. So for which values of x is the derivative of this function graph equal to 0? Wherever the slope of the tangent line is equal to 0, and that's at these minimum points and maximum points. So I'm going to say at x is approximately, I'm going to say, I don't know what, 2.2, and about -0.8. At those two x values, at negative zero point 0.8, somewhere there, and at 2.2, maybe somewhere there, that's where the graph has a zero slope tangent line. Okay, so we've done two things. We've looked at tables. We said if you're ever given a table, they're asking you for the derivative, but they want you to approximate or estimate it. Pick 2 points that are close to the one you want and find the slope using the difference quotient formula, which is just a slope formula. We looked at a graph. We said if they ever give you a graph and they're asking you to estimate the derivative, try to draw as best as you can the tangent line and then use 2 points that are on that line to estimate the slope. And now we get to, oh, look at this. Example 4, still using the same graph. Can you put the following in order from least to greatest? Maybe, but I don't know the slopes. And I don't have to know the slopes because, let's see, g prime of 0, that would be the slope right here. Well, I know that that's negative. G prime of negative 2, that's the one we found before. And I know that that's positive. And then G of 2, well, that's kind of close to 0. However, it is negative. So I'm going to say negative. Let me do another color. This one's negative close to 0. Right? We said that the derivative or the slope was 0 at 2.2. So close to that, that's pretty close to 0. Can I put these in order? In order from least to greatest? Well, yes. The really negative one goes first. The kind of negative one close to 0 goes next. And the positive one goes last. I'm putting them in order from least to greatest. Really negative, little negative, close to 0, and then positive. I didn't even know what the slopes were. But because I understand that the derivative is the slope of the tangent line, if they're asking me for a derivative, well, then I can just look at the slopes and kind of gauge where they go. G prime of negative 1. G prime of negative 1, that is up here, and that's still in the positive. I'm going to say positive close to 0. G prime of positive 3. G prime of positive 3 is positive, and then G of 1 is negative. All right, so if I had to put them in order, the negative one would come first. Oh, I'm sorry, I misread that. Look at this. G prime is the slope. G prime is the slope, but G of 1 is the actual value, and the actual value of the curve at 1 is 0. Oh, well, that's still coming first. G of 1, that's 0. And then I'm going to choose the one that's positive, but it's close to 0, so it's a little positive. And then I'm going to choose the one that's really positive as the maximum. So out of the 3, this is the order. 0 is the value. Little positive, close to 0, is the slope. Really positive is the slope. And I've put them in order. Not bad. If you have more questions on those, we'll talk about that and practice that in class. All right. Now we get to this. This is the easy part. If you have your calculator, we're given a function. If you can use your calculator and you're given a function, then we can figure these out fairly quickly. So I'm going to do example 5B and D, and we can do that right now. The natural log of x cubed plus 11. So I'm going to go over here. Here's what we can do. Well, let me do it one way with one problem, and I'll do it the other way with the other problem. So I'm going to go to math, option number 8. We're going to find a derivative with respect to x, and I'm going to type in the formula in terms of x. What was the formula? The natural log of x cubed plus 11. The natural log of x cubed plus 11. And I'm going to close it. So this is the function. We want to evaluate it at two x values. For letter B, we want to evaluate that at 0. And for letter D, we want to evaluate that at 5.1. So I go to my calculator and I tell my calculator, evaluate that at 0 first. There's our answer. Well, what do you notice about this answer? 9.095 e to negative 8. What does the e mean? That's a power of 10, 10 to the negative 8. That means I got to move my decimal 1, 2, 3, 4, 5, 8 times back. So it's actually 0.0000009095. That produces a decimal that's really, really small. And if I'm rounding to 3 decimal places, that is 0. So we're going to say that this is equal to 0. And now we're going to do the next one. I'm just going to copy paste. So I'm going to go up and up. I'm just going to copy by pressing enter. Once I shade it, I'm going to copy by pressing enter and then just change the 0 to 5.1. And there's the next one. We're going to be accurate to 3 decimal places. So we're going to say 0.543. And so that's going to be the answer that I write, 0.543. And you're done. You found the derivative. You found the derivative at specific points. You found the instantaneous rate of change by using the numerical derivative option on your calculator. And then finally, for this one, I'm going to try to show you a different way to do it. Square root of 3x plus 8, 1.2x plus e to the x. Let's see. So for this one, I'm actually going to save my equation in y1. So I'm going to make a fraction. And my equation was square root of 3x plus 8. 3x plus 8. And then in the denominator was 1.2x plus the exponential. 1.2x plus the exponential, which is e to the x, which is right there. Remember, e is a number, just like pi is a number, that's a decimal that goes on forever. E is a number that goes on forever. But I need to find the derivative. Specifically, I need to find the derivative of this function k. Let's find it at pi, and let's find it at e squared. Okay? Pi and e squared. So let's go to my calculator. Let me go back to the home screen. Let me erase this. We're going to do the numerical derivative. So we go to math, go to number 8, press an X. Since I already saved my formula in y1, if you press alpha trace, my bad, it gives you the list of all the y's. We have ours in y1, so I'm going to press 1, and the calculator knows to look for the equation that's in y1, and then I can just type in pi. Pi is second, and then this exponent button. Press enter, and we have our derivative there. And then if we want to find it at e squared, well, just copy paste, go back, and we can put e squared by just doing second natural log and putting a square there, and we can get that answer as well. So with the calculator, it's not that bad. You just have to tell the calculator what variable, what's the function, and then where do you want the instantaneous rate of change or the derivative calculated. It's going to give you a decimal, it's going to give you an estimate, but it's a pretty darn good estimate. And up to 3 decimal places, it's pretty accurate, very accurate. So I'm going to write the first one as negative 1.127, and the second one as negative 0.003. So negative 0.127. And then this one is, I'm going to put an approximation because we rounded to 3 decimal places, right? And then this one was negative 0.003. Is that right? Oh, I lost my negative 0.003. Yeah. And just like that, you found derivative values. So what is this telling us, by the way? This is telling us, for example, 5D, that this function is changing at a rate of 0.543 when x equals 5.1. That means it's going in an upward direction because my slope is positive. Versus this one, this function at x equals pi, at that moment, at x equals pi, it's decreasing because the slope is negative. So by knowing the positive, negative, or maybe even zero slope of the derivative of the slope of the tangent line, we can figure out what the function is doing. And that's going to come up in a later unit, probably unit number 5. All right, we did a lot. Let's take a break.